Well, now on for hopefully running to time, Equinox examines British Rail's new Class 91 high-speed locomotive Electra on the eve of its public unveiling.
This American-built Boeing 757 is a powerful tool in a commercial battle that rages throughout Britain daily. The combatants, air, road and rail. The passenger experiences speed, comfort and hopefully reliability. The airline, good payload, operational flexibility and a fast turnaround. It's technology that's being developed continually. Autoland, quiet large fan jet engines, and a steep ascent and descent capability. But it won't take you city centre to city centre.
Any more for Sheffield? Anytime ticket, Sheffield.
The coach will. Since deregulation, the long-distance coach operators have been wooing passengers with low fares, improved comfort and videos.
Oh, that's the second one on B16.
Coaches, like buses and trucks, are cheap and flexible to operate. Rock-bottom fares have encouraged more people to travel and made the market cutthroat. The coach must share its journey with an ever-increasing stream of trucks and cars. Car technology is also constantly developing. Comfort and economy are the manufacturer's principal weapons. The car will take you door to door, but the road system has been blighted by piecemeal planning and underestimations of capacity. Railway technology has been developing since Richard Trevithick built a train as a fairground attraction in 1808. Despite its Victorian origins, the train is still an efficient people mover. Unlike the car or the coach, the rail passengers expect split-second departure and arrival times, city centre to city centre. British Rail has been divided into business sectors. Intercity operates Britain's express trains. Subsidies from the taxpayer are being cut, and government is setting tough financial targets. With coaches, cars and planes competing with Intercity for the same market, powerful new technology must be developed to keep the trains running to time.
The tread brake delivery is still critical. Unfortunately,
these engineers are part of a project called Intercity 225. They are led by two men, Project Director David Rollin of British Rail and Mike Newman of GEC Transportation Projects. Their task, to build 140-mile-an-hour electric locomotives. The first must be delivered on February the 14th, 1988. Like the Boeing 757, they must deliver speed, comfort and reliability while being economical and flexible to operate. Each locomotive must have an operational life of 30 years. The locomotives are to be called Class 91, but are already better known as Electras. They'll be machines as fast and slick as a Ferrari, yet as strong as a bulldozer. Like all high-technology projects, there is risk.
It's no use letting the elephants through and stopping all the mice. The object is to identify risk, and the key areas of risk as I see them on a project is timescale, Can we meet the timescale? What are the key milestones in achieving that timescale? Technical risk, can we manage the engineering? Is it state-of-the-art? And if so, which parts of it need managing? Contractual risk, are we protected financially and legally in the event of any crisis or default? And last but not least is the business risk. Are we actually producing the right product and specifying the right product for the marketplace?
Intercity's principal weapon in today's marketplace is the high-speed train, or HST. It's a diesel-powered express deployed on the unelectrified part of the network.
Historically, the railways have tended to be engineering-led, technology push-led, in that it's been very much the railway engineers have said, this is possible. I'll give you a certain train, certain particular technical performance. You marketing people go out and sell it. Now, what you've had happen within British Rail more recently is particularly under the current chairman, Bob Reid, is a push towards the market-led railway of the market researchers, the commercial side of BR saying, we want a train that will do this, this and this. You engineers go and build it for us. That seems very logical and straightforward. The trouble is that very often the commercial side of an organisation may not actually know what is technically possible. Indeed, that happened with the high-speed train. The high-speed train almost developed out of a boardroom discussion over the advanced passenger train about how long it was going to take to develop. And one of the engineers said, well, I can give you a 125-mile-an-hour diesel train in a couple of years. What do you think about that? And the marketing people said, great, go and build it. And he did. They didn't realise that such a thing was possible.
British Rail's last engineering-led product became a fiasco. Britain has only one completely electrified trunk railway connecting London with the north, the West Coast Main Line. By the late 1960s, British Rail wanted to reduce journey times over its steep and curvaceous route north of Preston. Train speeds had already been raised as a result of studies into the behavior of train wheels. A train is not guided by the wheel flanges, but the shape or profile of the wheel tread that runs on the rail. This is known as the cone angle. It simply means that the wheel automatically returns to running with the rail at its center. This was the key for higher speeds on straight track. The research engineers turned their attention to active suspension systems as a means for increasing speed and passenger comfort on curving track. This tilting test rig was to develop into the Experimental Advanced Passenger Train, or APT-E. The gas turbine-powered APT-E was a complete departure from the evolutionary engineering practices that had previously been applied to railways. Aerospace techniques were employed in construction and a scientific approach taken to development. The train was eventually to run at over 150 miles an hour. In 1974, encouraged by its success, British Rail commissioned production prototypes called APT-P. They used much of the technical data provided by the APT-E team. Designed specifically for the London to Glasgow run, it had electric locomotives or power cars sandwiched between its articulated coaches. Active tilting suspension coped with the curves. These were to be the prototypes for the electric train for the 1980s. The development program dragged on for nearly 10 years, dogged by technical problems and a lack of management commitment. Because it was an engineering-led solution to a small part of the intercity network, It could not provide the basis for a head-on battle with planes, cars and coaches. The tilting train was dead.
British Rail set up an internal inquiry because there were some people that said it was just technically too complicated. Other people within British Rail said it was because we couldn't manage the project decently. And they actually got external management consultants in to have a look at this. And the management consultants basically came down to say that the technology was difficult but not impossible, and that basically British Rail were not capable of managing that sort of project. And that led to a great upheaval in the way in which British Rail do manage their more advanced technical projects. More or less all the consultants' recommendations were implemented, and a much stronger management structure was adopted for the successor project, which is the Intercity 225.
The failure of APT still haunts British Rail. The consequences of Intercity 225 running into similar problems has focused the minds of management and engineers. APT's demise has left a vacuum on the West Coast route that Electra was intended to fill. But the East Coast line is being electrified, and Intercity have decided to run their new locomotives here, on the straighter, faster track. Crewe, a town built for the railway by the railway. Its first locomotive chuffed from the works in 1843. But while those Victorians would have been mystified by the technology being used to develop Electra, much of the terminology remains the same.
This is a view of the locomotive with the fiberglass nose cone removed, showing underneath the bare skeletal steel structure. The large yellow area where the buffers are is the drag box. And this takes the pull from the locomotive train and is connected through the 3 grey pillars to the body. The green area is the collision beam, and the red area is the collision pillar, which only provides driver protection.
Before steel feels the breath of oxyacetylene, a full-scale equipment mock-up is constructed from wood.
This is the electronics cubicle, which is basically the brain of the system and responds to the driver's controls. Coming through here, we have the communications cubicle, which has 3 different types of radio in it. This is the rheostatic braking stack, which dissipates all the heat when the train is braking. Here is the converter cubicle, which provides the power to the motors, and subsequently the train locomotive goes forward. We've got an air reservoir here, which is for the air braking.
The mock-up allows maintenance, accessibility, and internal layout issues to be resolved, because changes on the production line can be costly and cause delays.
Cool. On this side, on both sides of the locomotive, we've now got blower motors for cooling the traction motor and choke, and the choke is a smoothing device for the motors. And then we come through to the driver's cab. This mock-up is particularly important for demonstrating the positioning of the instruments and the panel lights. Here we can see that the power control is placed within a reasonable easy reach of the driver. If at this early stage of design a change is necessary because items are in the wrong place, then it can be done at a minimal expense. Here you can see that we've got very adequate vision for the driver.
Most railway vehicles rest on trolley-like structures called bogies. Hidden by the platform, passengers seldom see them as their train rolls into the station. Yet, they are a critical component. They allow the long carriages to negotiate curves. Some bogies drive the train, but all regulate its comfort. They are a suspension rig with 2 suspension systems. The secondary between the coach body and the bogie frame, and the primary between the bogie frame and the wheel sets. A wheel set is 2 wheels and the axle they are fixed to. The dead weight or unsprung mass of each wheel set can be as heavy as a family car. The problem for the engineer is to minimize this mass. The less the unsprung mass, the kinder a vehicle is to the track. Most locomotives have powered bogies with traction motors which are axle-hung. This means that both the wheel set and motor are heavy unsprung mass. Seen from above as the train sits on the track, Electra's traction motors are suspended under the body, but within the bogie frame. A short cardan, or drive shaft, runs into a transfer gearbox, again mounted on the bogie. Two bevel gears take the power through a right angle. A hollow quill shaft connects the gearbox to the wheel set, with flexible rubber mountings. The axle of the wheel set runs right through the hollow gearbox and quill shaft. On the end of each motor is a disc brake. In this way, only the wheel set remains unsprung mass. Electra has two bogies with a traction motor to each of the four wheel sets. Individually, they have an unsprung mass of 1.7 tons.
Clever thing about the Class 91 compared with, say, the original idea of building an APT power car is that the bogie has been used to improve the performance of the loco as a whole. For instance, on the APT power car, the traction motors were mounted up in the body and drove the axles through very long cardan shafts, which was probably not a very good idea anyway. With Electra, GEC took the traction motors out of the body, slung them underneath the body in the space within the bogie, which is quite innovative, and then drive the bogie through, drive the wheels through very short cardan shafts. That has another advantage. If you move the traction motors below the body, it lowers the centre of gravity, therefore the train doesn't lean over so much when it's going around curves at high angles. It's a rather neat piece of design.
The thing you've got to bear in mind is it's got to be a very much more robust job than any car would ever get.
Shirt sleeve management at British Rail is done in a high visibility vest. John Prideaux, Director of Intercity, must set a business specification for the new train. It must be attractive to the passenger and economical to operate, helping his sector to meet its tight financial targets set by government.
I think that we needed another step forward in the attractiveness of our service to the customers. So we wanted a faster service, a more comfortable service. That the right direction to get that from was through electrification, and that the only way in which we could then perhaps justify such a programme, which is expensive after all, £350 million in today's terms, would be to provide a very efficient package.
Style is part of that package. Locomotives designed to attract the market's attention are not entirely new. It's a trick that has worked well in the past. Today, no railway can afford to build a new high-speed train without considering the impact of its looks. Warwick is not a town noted for its railway heritage. It's here that DCA, a design consultancy, are based. British Rail commissioned them in 1985 to develop some early proposals for an Electra package. But it's the styling of the locomotive that has received the most attention.
I'm very aware of the history of trains and locomotives, but I'm also aware that people's expectations of appearance, finish, quality has been jacked up over recent years, particularly through television advertising. I mean, you can't become another person when you go onto a train platform than you are when you go into a car showroom. And if you stand as a fond uncle with your small nephew there and say, this is the train which brought you from London to Edinburgh, and he stands at the front end and sees the headlights and the gleaming train going back from there, and then sees that the detail of the headlights is really so poorly carried out in comparison with the latest Ford popular car or whatever, then he's going to be disappointed. So inevitably, there is a higher standard of expectation in terms of finish and quality of excitement and the general presentation of the train.
There are a lot of engineers who tend to believe that it's a trimming that we can do without, but I think it's one of the many features, but a very important feature that we've got to meet, we've got to match. We have to tie these things in. The cowling that went along the bottom of the locomotive, which has changed. I think it actually looks better now that it's finished, but it has a purpose. It's there to direct air onto the gearboxes so that we can keep those gearboxes cool, or at least within the specified temperature, to make sure that they get their fair share of air as the locomotive runs.
Bounds Green Depot, London, on any weekday night. Many HSTs entering the depot have travelled over 1,000 miles during the day. Servicing them is a task of mind-boggling proportions. It's a world of giant car washes.
I haven't seen any shunters yet, either.
More seats to clean than in a dozen cinemas. More fuel than in a motorway service area. And running repairs to equipment that requires the help of cranes and air hammers bigger than machine guns. Each train has an inspection more thorough than an MOT. Three hours after arrival, they will leave, ready for more. Like aircraft, trains only earn money when they're on the move. HSTs go for 450,000 miles between overhauls. Electra will be pressed even harder.
It's just like driving a sports car. You start the wheels rolling, you'll see a driver just start it moving by putting it in notch 1. As soon as you've got the wheels turning, it's in full power, and then the power car does it. But you're driving it hard all the time, and you're braking hard all the time.
For diesels like these HSTs, operating conditions are on the edge. For Electra, with its simpler electrical systems, it's hoped that performance limits can be pushed higher with reduced service intervals. British Rail wants to operate Electra 21 out of every 24 hours. But for today, HSTs travelling at 125 miles an hour remain the mainstay on the East Coast route. Now they are over 10 years old and are sometimes so overcrowded that passengers stand between London and Edinburgh. Electra, hauling more coaches, will replace them. But this is only one element in the largest railway modernisation programme since the 1950s. In 1955, the now defunct British Transport Commission announced a radical modernisation plan. The steam engine was scrapped and replaced with a variety of diesel designs. Modern signalling systems were to be installed. And main lines, including the East Coast, electrified. Electric railways are the most efficient to operate. In Europe, the electrification of trunk lines has been widespread. It's taken over 30 years before British Rail has been allowed by government to spend over £300 million of its own resources and electrify the East Coast Main Line. East Coast Main Line electric locomotives will draw their power from copper contact wire, suspended above the track. This carries 25,000 volts of alternating current, purchased from the national grid. A pantograph on top of the locomotive makes contact with the energy. The train itself is only one component in the railway system. A train without track is like a ship without water. Electrification has made the East Coast Main Line the longest construction site in Britain. Over 33,000 support masts will carry more than 2,800 miles of copper contact wire. Progress has been rapid. Masts and foundations are planted and raised in minutes. Overhead wire systems are prefabricated into kits and scheduled to be erected between train passes. Because overhead wires must go under bridges, 148 have to be adapted or rebuilt while allowing the diesel trains to pass underneath. These efficient methods of construction have put the program a year ahead of schedule.
With electrifying a high-speed diesel train railway, a railway which already runs at 125 miles an hour, the opportunity for major journey time reductions is limited. But nevertheless, we are going to offer, by virtue of route geometry improvements and the introduction of electric traction, up to half an hour off the journey between London and Edinburgh.
In Britain, fast trains cut journey times. But the biggest reductions and cost savings are achieved by upgrading the old Victorian lines themselves. In Europe, it's a different story.
Let us show you the way to a woman's heart.
Far from innocent, Byzance, Barochas.
If you're longing for somewhere new and you're hoping to find the right place for you, don't worry now.
Why just keep longing for your ideal holiday when you can discover it in Dalton's Weekly? Britain's biggest choice of holiday accommodation, up to the minute every week. Ask your newsagent for Dalton's Weekly and discover your dream in Dalton's.
Roger, over and out. Okay, you guys, off your butts. We're pushing on to Carlin.
What? 30 miles through this jungle? On foot? Overnight?
With no chopper cover?
No ammo, no water, no supplies? With enough goons out there to fill the Rose Bowl?
Okay, okay. Strictly volunteers only.
Well, why didn't you say so?
Count us in, Sarge.
Sarge, count me out.
Oh, what? What? Let's move out.
Your best bet for a fuller flavour.
Darling Black Label.
Pure Cadburyness. Only from Cadbury.
Sign on the dotted line for a Scottish amicable pension, and who knows where it'll take you.
Villa in Spain, we adore you. We waited 20 years for you. Happiness, happiness, with the boat that we possess.
Where could a Scottish amicable pension take you? Just ask any independent financial advisor or ring 01 200 0200 for a pensions pack.
A successful relationship depends on understanding. One-to-one will help you understand more. It discusses openly your needs and his, and explores both sides of the relationship in a way that's refreshingly down to earth.
It's no longer a game. It's one-to-one.
Week by week, you can't get closer than one-to-one.
Symbole du futur.
Don Quichotte électrique qui glisse vers l'infini.
Puissance qui bouleverse.
Outil du temps présent aux multiples secrets.
Instrument des voyages.
The Europeans perceive their railways as a vital part of their national economic strategies. Most lines were originally built by governments to transport armies. Consequently, there is not the same web of track as built in Britain to link villages. By the mid-1960s, the French needed a new high-speed line to ease congestion on parts of the Paris-Lyon route. The result, TGV. This increased capacity. But France has the advantage of room to construct as well as sympathetic administration. The Germans have an overcrowded system too. Their government is investing heavily by building new lines for their high-speed train, ICE. Both these countries have trains that run on many miles of new dedicated track, unused by other types of traffic. But Electra will have to travel throughout the British system, sharing the rails with everything from coal to commuter. British Rail would like to build new lines similar to these in France and Germany, but there is neither the political or economic support.
In this country, the agreement to electrify the East Coast main line tended to be lauded as a great government enterprise, whereas in fact all that the government did was to give permission for BR to spend its own money. Now, if you go to the Federal Republic of Germany, the new high-speed lines that are being built there, all major electrifications, new marshalling yards, big investments like that are automatically financed directly once they've been approved by the Federal Treasury in Bonn. Granted, in France, the first of the TGV high-speed lines from Paris to Lyon, French railways had to build that entirely from their own resources or borrowed resources, as a result of which they landed themselves with a heavy debt, capital debt. But because of that, they protested they would not build a second line the same way. So the second line, the TGV Atlantique, the government are putting up 30% of the total cost. For social reasons, the government are also putting up a third of the cost of electrifying the main line from Paris to Brittany to keep the Bretons quiet. That sort of thing doesn't happen in this country.
This is the challenge of building the Class 91 locomotive, that it is ubiquitous and that it will make the maximum use of the existing railway which you have in Britain. I believe it is a more challenging task than building special locomotives to operate between two places and always along the same piece of track.
So Electra, a high-speed locomotive unique in Europe, starts to take shape. Crewe, June 1987. Work begins on the underframe. The underframe is a 9-ton steel bed on which everything either sits or hangs. It's fabricated in this jig of girders that can be rotated to improve access for the welders. Elsewhere, the load-bearing body sides are spot welded as two separate components before being joined to the underframe. The production line has been carefully laid out with each area of assembly color-coded. A system from the automotive industry known as just-in-time has been adopted. Parts arrive as they are needed instead of being stockpiled. This machine cuts components for Electra. Kits of steel are moved in pallets to be fabricated. The whole process mimics the sub-assembly techniques now commonplace on car production lines. Quality can be checked at each stage, improving the reliability of the component parts. Electra is not being built in-house by British Rail, but has been contracted out by competitive tender. Weighted business and performance specification documents were prepared for the competing manufacturers. The final choice was between 3 builders: ASEA of Sweden and the British manufacturers Brush and GEC. Competitive tendering offered British Rail performance guarantees and a good price.
It was a major change, particularly for the mechanical and electrical engineering department, and it required a complete change of thought about how one procured locomotives for, or anything for the railways.
GEC Transportation Projects won the contract, and are the main contractors. They are manufacturing the electrical equipment. British Rail Engineering, BREL, have been subcontracted by GEC to build the body structure and fit it out. For BREL, now being divorced from British Rail and a candidate for privatization, Electra is a vital contract. GEC in Preston are manufacturing the locomotive electrical equipment. This is one of the 4.5-ton traction motors. There are 2 kinds of electric current: AC, the sort which is in the home, and DC, the type of power which comes from a battery. This motor is a direct current DC machine. The AC power, collected from the overhead line, is transformed in the locomotive. Cost-effective AC motors for high-speed railways are still at a development stage. This motor is state-of-the-art DC. Inside electric motors are 2 principal components: the armature that spins and the surrounding fixed windings. In Electra, the amount of current sent to both can be varied independently by a control system called SEPEX, separate excitation.
The feature that most people would recognise is that it's rather like an infinitely variable gearbox. Very smooth, no equivalent of gear changes, which in railway terms is called tap changing on the traditional style of transformer. So SEPEX is really a smooth power control.
This motor is rated at about 1,500 horsepower, and in fact it'll be the most powerful motor running on British Rail. One way of appreciating how far advanced it is to compare it with that one, which is an existing design, very successful, but something like 15 years old. These 2 machines, in fact, weigh almost exactly the same, and yet this one is more than 30% more powerful.
Like the electrical equipment, the bogie and its powertrain are mocked up in wood to help engineers debug the now familiar components.
Well, here we are underneath the bogie with the traction motor suspended from the vehicle underframe, driving through a cardan shaft, the right-angle drive gearbox, which will be here over the axle, then driving through a flexible quill to one wheel set. The other wheel set at the other end of the bogie is driven through this traction motor, again suspended from the vehicle underframe, with its associated disc on the back of the armature shaft. There was some thought that the disc pads would be difficult to remove, but this mock-up has shown that by putting a hole, an access hole in the underframe, we can withdraw the disc pads through the underframe.
When power is applied to the motor, the full strain of its 1,500 horsepower is placed on the 2 gears in its right-angle drive gearbox. This is the most critical component in the locomotive.
Yes, it is a critical area. Yes, it is something being identified as a critical area by BR and GEC. And obviously a corresponding amount of work has gone into it. They've had 2 drives being evaluated from 2 different manufacturers, very comprehensive testing, back-to-back testing to make sure I would have thought that when the trial running starts going, there'll be a lot of people looking very hard at this to make sure that out on the real world of the track, it performs as advertised.
We've looked particularly at the lubrication of the gears and the gears themselves, the ear tooth contact, as well as the bearings, and again the bearing lubrication. All of these issues have been very, very important to us. We did actually have one more pragmatic type of problem where some seals actually came into contact and there was a rubbing and blue smoke. If we'd found that on the track, it would have been catastrophic. So the testing itself has revealed very pragmatic answers to problems, but also it's given us some insight into how the gearbox is working, and working very satisfactorily.
David Brown and the German company Voigt have been subcontracted to build the gearboxes. The German firm experienced early difficulties with the gear teeth profiles, but these now seem to have been resolved. GEC Stafford Research Labs. A gearbox is under test on a 4-square rig. 4 drive shafts are formed into a square powertrain with a gearbox at each corner. Torque is applied to the rig to simulate loads like a 700-ton train and then run at speeds representing 160 miles an hour. The hope is that any gearbox weakness will be forced into the open on these rigs instead of Intercity's timetables. At GEC Traction in Preston, a locomotive with no wheels or body has been assembled. Yet this locomotive can run between Edinburgh and London at 140 miles an hour. It's called a combined test rig. All the electrical control gear is tested. It's a much more scientific approach than running a pre-production locomotive on the track. The test is run in real time. The computer tells the engineers that the train, with its 12 vehicles weighing 700 tons, is now travelling at 140 miles an hour, near Selby in Yorkshire. Not a teacup rattles. Out on the track, 125 looks like this.
The main purpose is to set the electronics up so that they're controlling the traction system. So we're not necessarily looking for things that are wrong. We're trying to make them right in the first place. And we can check the ventilation to make sure that the cooling air systems work properly over the motors and transformers. Those are the sort of things that we would look for. But occasionally we do actually find faults and we get a puff of blue smoke. As I say, it's a lot cheaper to have puffs of blue smoke out here than it is out onto the track.
Ever since the demise of steam, the driver has had less control over the direct functions of the locomotive. Just like an airline pilot, the driver uses controls that control other controls. Electra is controlled by thinking electronics. Semiconducting thyristors allow the smooth application of power to the motors. They are an industrial version of the living room dimmer switch. Brake control systems can instantly turn the traction motors into high-speed brakes by putting them under load. In effect, turning them into generators. The heart of Electra is this microprocessor.
Our microelectronics in the control systems of the Class 91 locomotive are effectively the brain of the system. They have built into the memory a profile of what the motor looks like, and they decide every few thousandths of a second when to send a pulse to one of the thyristors to make it fire, and that controls the flow of current to exactly the requirements under the circumstance. Now, the microelectronics does much more than that. It stores information for the maintenance engineer. It provides information to the driver, all, if you like, outside the circuit, but inside the circuit it is actually driving the locomotive against the basic instructions provided to it by the driver's controls.
You can tell the microprocessor, today we're going to be a 140-mile-an-hour train up the East Coast main line. You can then say to the microprocessor, tonight we're hauling an 800-ton sleeper, and it will alter the characteristics of the motor. So it's a very important technology.
Electra has a driving cab at each end, but it will form a push-pull train. This requires another control cab at the opposite end of the train to the locomotive. For British Rail, this means the time the train spends in a station can be reduced. Only the driver need change ends and not the locomotive as well. The unpowered driving cab is called a driving van trailer, or DVT. It has capacity for carrying mail, parcels, and the train guard. The DVT and the new coaches known as Mark IVs are being built by Metro Camel of Birmingham. Like GEC with the locomotive, they won the contract by competitive tender. The Railway Technical Centre, Derby. A DVT body shell arrives to be tested for strength. Like all modern railway vehicles, it's constructed as a very strong steel box.
The whole series of tests will take about 13 weeks, and that comprises approximately 8 different loading conditions, loading at a buffer level onto the draw gear, onto the crash structure at each end of the vehicle, onto the roof, vertical loading representing the payload and the equipment weight in the vehicle, and diagonal loading representing corner collisions, say with the vehicle hitting a bridge abutment or something of that nature.
The Mark IV coach is also strength tested at Metro Camel in Birmingham. A body shell is loaded with weights and wired with hundreds of tiny strain gauge sensors. In a hydraulic Iron Maiden, the shell is squeezed by 200 tons of force at either end. The results are tiny distortions in the body shell. The engineers can see where extra strengthening may be required. The unpowered bogies are the most critical components in the Mark IV coach. It's another area of risk. Smooth ride is where the passenger makes contact with the technology. Mark IV is specified to ride at 140 miles an hour, as well as these Mark III coaches at 125. Computer simulation tests were carried out on 2 bogies, one made by the Swiss manufacturer SIG, the other by British Rail Engineering.
Well, at the time of tender, we offered either a British bogie, which was under development, or what we regarded as a proven European bogie. In the end, the British Rail, the board, took a decision that they did not want to be in the business of development, that they wished to use a proven product. The SIG bogie, which, by the way, after the first few, will be manufactured here at Metro Camel, the SIG bogie has been tested in Germany at high speeds and at speeds higher than we are building these vehicles to. And the same family of bogies is already in use in Switzerland on their equivalent of the Mark IV coaches.
There have been cases in the past where a bogie which seemed to perform well on the con, which undoubtedly did perform well, has been imported to this country and put under coaches for operation on British Rail, and has performed very differently indeed. There are considerable and significant differences between the characteristics of track in this country and track on the continent.
Trials have been conducted with 2 prototype bogies under a test coach running on the main line. But until the SIG bogie is fully tested and tuned, the ride quality of the coach remains open to question. Resolving bogie performance has delayed coach delivery by 5 months until the 2nd of April 1989. The speed of electrification has meant electric services to Leeds in 1988, a year early. This creates a problem. Electric line, but no trains. British Rail originally intended to test Electra with empty loads. Instead, they will haul HST coaches and a power car on scheduled services to fill the gap. They gain more intensive service experience, but it's a risk. A risk to Intercity of denting the business-led image, and a risk to the passenger of being in a train not running to time.
Well, I don't think it's technically disastrous, but it's embarrassing. One can imagine what the press will make of it. You know, wondered loco goes in with yesterday's coaches or something like that.
The locomotive building is running to time. At Brell, Crewe, the first 5-ton locomotive bogie frame is mated with a wheel set, flexible drive and gearbox. This assembly is held in a special adjustable cradle.
I'll locate the spring, so we need to go. Can you go that way, George?
As the frame is lowered, 28 fixing points must locate with precision.
Yeah. Oh.
Under the locomotive, a traction motor body has also been offered up to check for fit. Once mechanically complete, each of the first production run of 10 Electras will have their systems checked on a static test rig at Crewe. Finally, the livery will be applied.
As I see this locomotive, we're building effectively 10 prototypes. Then this is for the Leeds service on the East Coast Main Line. Then we're following with a further 21 of trains that go through to Edinburgh. Now we shall operate these 10 for 1 million miles, cumulative miles between the 10, before we proceed with the second 21. Any bugs and difficulties we find, we shall retrospectively correct on the first 10 and include into the design of the second 21. So we've gone to a halfway house of a prototype.
BR has to learn to operate and maintain what is now a very high technology locomotive. And my guess is that if troubles arise, it will be in that process of learning to service and operate this vehicle.
The earliest we can prove these locomotives in endurance running, the better. We must be confident that we don't expose ourselves in the marketplace with a product that's anything less than reliable and to specification.
For Electra to be truly effective in the marketplace, the same ruthless and objective approach taken by the engineers must now be applied by the marketing men and operators. However good the train, for the passenger, it's the point of contact that counts. Unsympathetic staff, dirty coaches, closed buffet cars, uncompetitive and confusing fares do not make rail travel attractive, even if the train is running to time.
Tomorrow